Dear students, we have learned already the problems with age and sex data in India and also in many other countries, particularly in the developing countries. We have also learned how to adjust. We have also learned some methods to evaluate this data and measures to understand the magnitude of errors. In this section, we will be learning how to adjust this data in case we find errors. We have learned several measures which will give you idea about the errors in this data, like Mayer's index, Whipple's index, even joint score, rectangularization index, and so on. So, in this session, we will explore some methods for adjustment of age and sex data, and we will give you some examples to show from the Indian census how such adjustment can be done. Let us first look at the age and sex data, and we have already studied how important is age and sex data in demographic analysis. Therefore, any analysis done without looking at the quality of the data and without making proper adjustment, there are possibilities of serious errors which can create several issues with regard to the demographic estimates. Age of an individual at any time is defined as the number of completed years lived by that individual at the time, or it is the age at last birthday. And adjustment in age distribution is very essential because of many types of errors in census and surveys of almost all developing countries in general and India in particular. We have already seen how age heaping taking place in India and how digit preference affects the age distribution. We have also seen how actually the sex composition of the population is affected by under-enumeration of the females, particularly of certain ages. Therefore, adjustment of age distribution is critical for any demographic estimation. The corrected age distribution is very useful for not only demographic analysis, but many times for the economic and market research and so on. The more accurate the data of age distribution, it will be much more useful to understand the future scenario, because the future population projection also depends completely on the age structure of the current population. If the data of the current population is distorted by age and sex, naturally the population projection of the future will also be wrong, because it is starting from a wrong age distribution and sex distribution data. Young population are normally under-enumerated, as we have already seen in the previous session, and advanced age population try to exaggerate their ages. In this session, we will deal with errors in age distribution of age particularly up to 59 years, because we have already looked at the errors and adjustment of child and old age data to some extent. Even in the grouped data in 5 years of age group, there are serious errors with figures shifted from one age group to the adjacent age group. Thus, we need an adjustment for have a real age distribution of the studied population. These are primarily called the smoothing process or smoothing procedures, and a number of such methods are available in the literature. Therefore, the normal age distribution, which is derived from census and surveys in the country, will be unsmoothed, meaning there are wild fluctuation in different age groups, different ages, as well as across sexes. But if the procedure is adopted and a smoothing procedure is done for the data will become a smooth data, which then can be used for different analysis. But any such methods are also not without any assumptions. So one has to be careful and understand what are the major assumptions which we make when we use such data for adjustments. The different methods of adjustment assumes that the total population reported in the census is correct and the problem is only in the age distribution which needs correction. Perhaps we have already seen this assumption need not necessarily be true, because there are sex differentials in the registration and underreporting. There are also underreporting of certain age groups, particularly at the younger ages. On account of all these, it is possible that even the total population enumerated is not accurate, but no adjustment is made in these procedures adopted, because the procedures which will be discussed now will primarily be concerned with the age distortions rather than age, not reporting of age or age. The methods which will be discussed now will primarily discuss on the age misreporting rather than not capturing that event. Let us look at the rationale of smoothing age data, because planning and policies require invariably accurate counts by age, otherwise the planning and policy process will get adversely affected. For example, children entering into school system is essentially needed if one needs to plan for the educational system of a country. Young males reaching military at a particular age is need to be counted if we have accurate data of the young males in the country. The qualifications for older ages for the public benefits systems or social security benefits needs to be understood if we have exactly accurate information on how many persons will be reaching a particular age in a particular year. So, any flawed data on age, sex in these ages will have adverse impact on the future projection as well as for the real estimate of the number of people who are at the younger or who are at the older, even at the adult age groups. Such flawed age counts used as denominators in demographic rates may also bias the demographic estimates. Naturally, because of the wrong data and wrong estimates, the entire planning and policy process might get affected because of the lack of data, in lack of good quality data in the systems. Smoothing techniques may be lighter or stronger depending on the formulas that one construct for an average. Light smoothing, the formulas that give greatest weight to what was reported for the age group in question and smallest weight to the adjacent age groups. But in strong smoothing, formulas that give greater weight to the adjacent age counts and over wider age intervals. Resulting pattern does not follow any contours of reported data as well as lighter smoothing. Therefore, smoothing can be undertaken depending on the assessment or the evaluation of the quality of data of a particular region or a particular country. In case the evaluation of the data, age data, it is found that it is highly erroneous, one perhaps has to adopt a stronger smoothing technique compared to a lighter smoothing techniques. But in case the evaluation of the data quality, it is found that it is of a lesser intensity, then the lighter smoothing techniques can be adopted so that the age data get adjusted. Let us now discuss some of the measures which can be adopted for smoothing age data. The first one is the method of moving average, which is expected to be a stronger method in smoothing the data. In this method, the corrected population size at any point, any ages I, is considered to be equal to the average of the three observed values adjacent to the age I. Hence, age 1 minus I minus 1, I as well as I plus 1 will be taken, and a moving average of these three will be considered for smoothing the data. Hence, if Pi, P is the population at a particular age group I, for instance, if it is 15 to 19, the corrected Pi values will be Pi minus 1, that is I minus 1 will be 5 to 9 age group, and Pi, which is the 10 to 14 age group, and plus Pi plus 1, which will be 20 to 24 age group. An average of these three population will be considered for as the corrected values for the Pi when I is 15 to 19, 10 to 14 age group. This method is termed as 3-year moving average of the observed values of the population in age group I minus 1, I and I plus 1. This method of smoothing counter the problem of some person report their age I while their actual age is I minus 1, or in some cases some people report age as I when their actual age is I plus 1. Thus, this age shifting from one age group to the another age group can be eliminated through a 3-year moving average method. The method of moving average also can be computed for a 5-year period rather than a 3-year period. This procedure in case of 5-year age group is as follows. It is Pi again, suppose Pi represent 20 to 24 age group. We also need to get Pi minus 1, that is in the 15 to 19 age group population, plus 2 into Pi, where the Pi value of 20 to 24 age group is multiplied by 2, plus Pi plus 1, that is the subsequent age group 25 to 29 age group, and in this case this will be divided by the 4. So, the corrected Pi value will be Pi plus 1, 2 into Pi, and Pi plus 1 divided by 4. The presence of severe errors in reporting of age data, when it seems that errors are spillover in more than one adjacent ages, a 5-year moving average is generally used for smoothing, and in such cases you would have Pi minus 1 and Pi minus 2. It means taking 2 preceding age groups and also taking to succeeding age groups and dividing it by 5. The method is similar to 3-year moving average, except that in this case 5-year moving average is computed. This, in case even further, if data is of extremely poor quality, it is also possible that a 11-year moving average is computed to adjust the age distribution. So, we would take an example and give you how do you compute a method of moving average to adjust the age data. For instance, if you have Pi is of a particular age, the previous age group population and succeeding age group population, and 2 into the Pi value divided by 4 will give you a Pi, a score, a corrected population of a particular age group. In this case, it is considered as 10 to 19 age groups. This is the moving average, which is often used for a simple analysis, but advanced type of smoothing are also available to have a better result compared to the simple moving average. Therefore, the second method, which is often adopted for smoothing the data, is known as polynomial and other curves, which are used for adjusting the age distortions. The polynomial is mostly used and widely accepted procedure for smoothing and adjusting age distribution data, particularly in case of developing countries, and this is done through fitting a mathematical curve. The mathematical curves utilized for obtaining an estimate of population at any particular age group ranges from 3rd degree to 5th degree polynomial, depending on the extent of errors we expect in the data. The extent of errors is known based on the evaluation methods and based on several methods we have already learned to compute the extent of errors, like Mayer's index, Whipple's index, or UN adjusted score. Since, as we know, the population growth follows a logistic curve, the polynomials used for smoothing of age distribution performs on a logistic function. However, the polynomial function of a population at any given age x can be written as Px is equal to a0 plus a1x plus a2x squared plus a3x cube. This is a 3rd degree polynomial because it goes up to x cube, indicating that we would look at a 3rd degree polynomial, and in case the adjustment is needed for a 5th degree polynomial, it will be Px is equal to a0 plus a1x plus a2x squared plus a3x cube plus a4 x4 x raised to 4 plus a5 x raised to 5. The constant term, which is unknown here, a, can be estimated from the 4 successive observations and 6 successive observations in terms of the 5th degree polynomial and 4 successive observations in terms of the 3rd degree polynomial. So, as we have pointed out, it will be using a logistic function, and the logistic functions are always known as Px k divided by e raised to a plus bx, which is the normal logistic function used for the adjustment. And in this case, the constant term can be estimated from the 3 adjacent value which is available in the population figures. The formula is based on fitting 2nd degree curve through a successive 5-year age groups. So, PI corrected will be, there are also other methods to smoothen the data which is available other than the polynomial function which was learned now. The next one formula is based on fitting a second degree curves through 5 successive 5-year age groups. In that case, PI corrected will be equal to minus 5 PI minus 10 plus 4 into 5 PI minus 5 plus 10 into 5 PI plus 4 into 5 PI plus 5 minus 5 PI plus 10 divided by 16, where the population in the age group I plus 4 is considered. All these can be given through an example. Well, let us take an example where in this table 0 to 4, 5 to 9, 10 to 14, 15 to 19 and 20 to 24 population is given. Therefore, in case we need to correct population in the age group 10 to 14, that is P 10 to 5-year age interval, that is 10 to 14 is equal to minus of that population in that particular age group plus 4 into the population in that particular age group plus 10 into population in the that age group into 4 into population into this succeeding age group and divided by 16 is equal to, you would get a corrected adjusted population for the 10 to 14 age group. There are also other different methods to estimate and adjust the population. One is called Carrier-Frag formula. This method generally used for splitting the 10-year age group data into 5-year age group, assuming that 10-year age data are corrected are more accurate than the 5-year age group data. So, assume if the 10-year age data is more accurate than the 5-year, a mathematical function is used to split the 10-year age group into 5-year age group rather than taking directly the available 5-year age group from the census of surveys. The formula is simple, which can be easily adopted and then can be estimated the corrected population at a particular age group. The examples are also given, and applying this formula you get, for example, for the population into 25 to 29 age group, the corrected population based on 20 to 29, 10 to 19 and 30 to 39 population which are available in the 10-year age group, you would make adjustment and finally get a population, corrected population for the population 20 to 25 age group as the new one, 14,12,893 instead of 27,39,846, which was the earlier figure. There are other methods which are used by Karup, King and Newton formula, which is again an adjustment to the earlier methods. This is also another formula to split the 10-year age group into the component of 5-year age group. The Karup, King, Newton formula assumes a quadratic relationship among the each 3 consecutive 10-year age groups. The interpolation of formula is mathematically equivalent to the Lagrange's formula, but is much more efficient. One of the most important features of the formula is that one can gradually increase the support data without recomputing what is already computed. So, the examples are given how we can derive a new estimates using this formula and adjust the age group for the 25 to population in the 25 to 29 age group from the information available for the population 10-year age group for the succeeding and preceding age groups. The last method which is discussed is the Arrigha's method, when 10-year age groups to be separated is the central group of 3, that is, if the assumption is that the second degree polynomial passes by the midpoint of each of 3 consecutive 10-year age group and it integrates the 5-year age group, Arrigha's method is used. Here also the examples is given for the 25 to 29 age group to make adjustment through a second degree polynomial. Finally, all the methods which we have learned here are smoothing techniques which assumes different mathematical function from the simple moving average to second degree or third degree polynomials or other logistic functions and other functions which can split the 10-year age group into 5-year age group, assuming that the 10-year age group data is of much higher quality than the 5-year age group. All these functions will enable us to get much more smooth age distribution, which can then be used for further analysis for the demographic estimation and computation of rates and ratios, which will improve the quality of estimation and also the future projection. Thank you.